Hello everybody, this is Arya. I'm bringing you this presentation with Masa and Kevin. Now chances are if you found this video, you're currently in Mosh's Math1B class, and you're in need of reviewing all the techniques of integration. If that's the case, this is the perfect video for you, because us three are going to be reviewing all of the main concepts of Chapter 5 to help you prepare. Now if you look on this slide, there's a good list of 12 techniques of integration that we're going to be going over in the following minutes. So the first thing we're going to be looking at are the list of basic integrals. Here's a nice chart that illustrates some of the common ones that you need to know. Now something interesting about this chart is that the way it's written, it's written as a list of derivatives on the left and functions on the right. But it can also be viewed as a list of functions on the left and a list of antiderivatives on the right. When you recognize this fact, you suddenly see the inverse nature of integration and derivation, which is quite interesting. But beyond that, all you really need to memorize are this list of integrals and derivatives, because it's going to be key in solving the problems in the rest of the chapter. Now let's look at the first real technique of integration that we're going to be looking at. That's use substitution. Here's an example to illustrate. Let's imagine that you're trying to integrate tangent x dx. Now, as we saw, tangent x dx is not a basic integral, so we're going to have to think of another way to approach this problem. Let's imagine splitting tangent x into sine x over cosine x. So if we do this, one thing we could do is set cosine x to equal a random variable. If we do that, we can set that as u, and then du, which is a derivative of that, is going to equal negative sine x dx. Now plugging that back into the original expression, we get the integration of negative du over u. Now if we remember that the derivative of ln u is equal to 1 over u, we can use that to actually integrate that function and resolve it to negative ln absolute value of u plus c. Don't forget the plus c. Now that equals negative ln cosine x once we substitute cosine x for u, plus c, of course. Now here's a critical step. Remember that ln and that negative ln of u is equal to ln of u to the 1 over u. So here we basically get ln of the absolute value of 1 over cosine x, which is the same thing as ln absolute value of secant x plus c, and that's your final answer. Next up, trig identities. As you can see, we've compiled a nice list of some trig identities that are going to be really important for you guys to remember, but instead of just going through all of these right now, let's look at an example. So let's take the integration of tangent cubed x secant x dx. So as it stands, the integrand here is a product, which is going to make for a much more complicated process in order to integrate it. So is there a way to maybe make this simpler or make it not a product? There actually is a way. So if we pull out tangent squared x, we can use our identity to substitute secant squared x minus 1 for that to make the integration a bit simpler here. And so what we do is we distribute tangent x secant x dx, and we get actually two integrations. So it may look like we're making it a lot more complicated, but actually check this out. The first integration we can solve using u substitution, setting secant x as u and secant x tan x dx as du. And then the second integration is actually just a basic integral. Tangent x secant x is, as we just saw, is a derivative of secant x. So we use u substitution on the first part, and we get the integration of u squared du minus secant x. Now simplifying this and integrating, that becomes u cubed over 3 minus secant x plus c. And then substituting secant x back in for u, we get your answer. Next up, integration by parts. So as we saw before, it can get a little bit complicated when you have to integrate a product of two functions. But sometimes you have no other choice. You have to integrate that without any other way of representing it. So as we can see in this formula here, one way of doing that is to set the multiplier as u and the other multiplier as dv. And then if once we represent it like that, we can represent the whole integral as the product of uv minus the integration of v du. Now this formula is derived from the product rule, which you learned in Math1A, so we're not going to get into the derivation right now. We are going to look at an example. So let's look at the integration of cosine x e to the negative x dx. So let's set cosine x as u and e to the negative x dx as dv. In a following slide, we'll explain how we selected these, but for now suffice it to say that this is what you should do. So using u and that dv, we can represent the original integral as negative e to the negative x cosine x minus another integral, that of e to the negative x sine x dx. So now we have to integrate that one again. So we're going to use a very similar technique. Set sine x to equal to u and e to the negative x dx as dv. So resolving that one as well, we get altogether negative e to the negative x cosine x minus the quantity negative e to the negative x sine x minus the integration of negative e to the negative x cosine x dx. Now you might be saying, hold on here, that last integral is the same as the original, so what's the purpose? Well, let's look at this whole thing this way. This entire expression that we've just found is still being set equal to the original integral. So why don't we just add negative cosine x e to the negative x dx to both sides? If we do that, we see that the whole equation becomes 2 times the integral of cosine x e to the negative x dx equals negative e to the negative x cosine x plus e to the negative x sine x. So now dividing 2 by both sides, we actually get an expression that represents the integration of cosine x e to the negative x dx, and that's our final answer. So here's a slide that is quickly going to show how we came up with those u's and dv's. So when you're looking for which of the two functions should be u, there's a hierarchy. So ideally you want u to be an inverse function. If there is no inverse function in the integrand, you can go with a polynomial. And if there are neither of those two, you can go for either an exponential or trigonometric function. In the example that we showed, both of the functions in the integrand were either exponential or trigonometric, so the order in which we choose u didn't really matter. But in following examples, you can choose based on this. Now let's look at trigonometric substitution. This is somewhat similar to trigonometric identities, which we looked at before, but it varies in one way, and that is how you apply the identities. So when we use trig substitution, we're going to be actually starting with x, or another variable, and substituting that for a trigonometric function. So the two main identities that we're going to be using here are 1 minus sine squared x equals cosine squared x, and 1 plus tangent squared x equals secant squared x. Now let's look at how you use that. In a general case, let's imagine you have a minus x squared. So if you notice that looks kind of similar to 1 minus sine squared x. I know that's a bit of a stretch. You can substitute square root of a times sine theta for x. If you do that, you get, after you square it, a minus a sine squared theta, and pulling out the a times 1 minus sine squared theta. And then we can substitute cosine squared x for that quantity right there to make it a times cosine squared x theta. So let's look at a real example here. Let's imagine you're trying to integrate from 1 to infinity square root of x squared minus 1 dx. So we should notice that x squared minus 1 looks kind of similar to secant squared theta minus 1. So that's how we're going to substitute. We're going to set x to be secant theta and dx to be tangent theta secant theta d theta. So using that substitution, we get the integration from 1 to infinity of radical quantity secant squared theta minus 1 times tangent theta d secant theta d theta. So substituting tangent squared theta for secant squared theta minus 1, and then taking the square root of that, we get the integration from 1 to infinity of tangent squared theta times secant theta d theta. So then we have to actually go back to secant theta. So we take tangent squared theta to be secant squared theta minus 1, and distributing, we get the integration from 1 to infinity of secant cubed theta minus secant theta d theta, except we forgot one thing. That would be infinite limits of integration. So we should remember that we resolved the previous equation to the integration of 1 to infinity of secant cubed theta minus secant theta d theta. Now, our problem here is that we can't really leave infinity as one of the limits of integration, because mathematically it doesn't really make sense to integrate a function over infinity, right? It's just graphically that doesn't really make sense. So we need to deal with infinity the way we usually deal with it, which is by using limits. So we can represent this integration as the limit as a goes to infinity of the integration of 1 to a of secant cubed theta minus secant theta d theta. And then we distribute that new limit integral to make it a bit easier to integrate. And then once we integrate both secant cubed theta d theta and secant theta d theta, our next step is to undo our substitution and bring this equation back in terms of x. So that should be relatively simple, remembering that our original substitution was x equals secant theta. So if we use some inverse trigonometric functions and the like, we can revert this back in terms of x. And then we simply apply our limits of integration. So we get this long jumble, and this is all in terms of a. So afterward, we have to use the limit and see where all of these go at infinity. And once you add this all up, this entire equation will go to infinity when a goes to infinity. All right, now we're going to look at partial fractions. This is simply borrowing a technique from previous math courses and applying it to solving integrals. So when we will use partial fractions when the integrand has a denominator that is the product of several terms. In this case, we're looking at the integration of 1 over x squared times x plus 1 dx. So the first step in using partial fractions is isolating the integrand. In this case, 1 over x squared times x plus 1. So the idea of partial fractions is to represent that integrand as the sum of several fractions. And each fraction is going to have the denominator that is a factor of the original denominator. So to break it down, the original denominator, x squared times x plus 1, has three factors: x, x squared, and x plus 1. So using partial fractions to represent the integrand, we can set it as some number a over x plus some number b over x squared plus some number c over x plus 1. Now multiplying both sides by the least common denominator of x squared times x plus 1, we see that this equation becomes ax times x plus 1 plus b times x plus 1 plus c times x squared equal to 1, or recognizing that 1 has no quadratic or linear terms, 0x squared plus 0x plus 1. So combining like terms and solving this, we can see that a will be -1 and b and c will both be 1. So now, what does this mean for solving the integral? Well, we can represent the whole integral as the integration of these three fractions. So that's going to be the integration of a, or -1, over x dx, plus the integration of b, or 1, over x squared plus times dx, plus the integration of c, or again 1, over x plus 1 dx. So integrating all three of these fractions, we get negative ln x minus 1 over x plus ln x plus 1 plus c. and that's your final answer.
Okay, now it's time to look at completing the square. This is going to involve applying a technique learned in previous math courses to solving integrations. So the gist of completing the square is manipulating a quadratic polynomial to make a perfect square. So let's see how this will work when applying it to solving integrations. So let's imagine you're trying to integrate dx over 2x minus x squared. Off the bat, we can recognize that the denominator, 2x minus x squared, looks a bit like a perfect square. It looks like negative 1 plus 2x minus x squared. We're just missing the minus 1 in the denominator. So why don't we just try adding and subtracting 1 to both the numerator and the denominator? What happens when we try that? Well, the numerator will just stay the same because adding and subtracting 1 leave no net change. But that allows us to rewrite the denominator as 1 plus negative 1 plus 2x minus x squared. So after distributing a negative and factoring, that leaves us with the integration of dx over 1 minus quantity x minus 1 squared. So once we get it to this point, the rest is pretty simple. We can just use substitution. So let's set x minus 1 as u and dx as du. When we do that, we're left with, rewriting this integration, we're left with the integration of du over 1 minus u squared. So if we remember that the antiderivative of tangent hyperbolic inverse is 1 over 1 minus x squared, we can solve this integration and set it as tangent hyperbolic inverse u plus c. And then simply undoing the u substitution, we get our final answer of tangent hyperbolic inverse x minus 1 plus c. Okay, next up is eliminating roots. Now, if you've made it this far into the video, you probably deserve a bit of a mental break. So this is perfect timing because, let's face it, eliminating roots is probably one of the simpler methods of integration that we go over. On the other hand, though, it would definitely be a mistake to take anything lightly in this class because, as we know, you do not mess with Mosh. But anyway, let's just look at an example of how to apply this technique to integration, shall we? So let's look at the integration of dx over x plus the square root of x. So the best initial approach to this problem is u substitution. You can set x to be u squared, or conversely, you could set u to be the square root of x. Either way, it makes no difference because dx becomes 2u du after you differentiate both sides. So substituting this into the integrand, we get the integration of 2u du over u squared plus u. And pulling u out of the denominator, we get the integration of 2u du over u times quantity u plus 1. Now at this point, because we're integrating and we don't have to worry about losing roots, if we have a variable in both the denominator and the numerator, we can simply cancel the terms. So that leaves us with 2 times the integration of du over quantity u plus 1. Now, if we also remember that the antiderivative of ln x plus a constant is 1 over x plus that constant dx, we can solve this integration as 2 ln u plus 1 plus c. And then undoing the initial substitution, we get 2 ln quantity the square root of x plus 1 plus c. And that's our final answer. I'm afraid if we consider roots elimination to be a mental break, sine-cosine elimination is probably going to be a bit of a mental CrossFit workout. So let's not waste any time and get right in. But before we look at an example of sine-cosine elimination, it's time for a story. So one day, someone much more intelligent than me came up with the approach of looking at a right triangle with an acute angle of x over 2. So he decided to set tangent of that angle to be u. Now that means that in this triangle, the side opposite to the angle must be u, and the side adjacent to it must be equal to 1. And that means the hypotenuse must be equal to the square root of 1 plus u squared. Now, if we do some math with this original equation, we can get x over 2 to be equal to tangent inverse of u. And also, we can get dx to be equal to 2 du over 1 plus u squared. Now, the other thing we can do with this triangle is find sine and cosine, right? So we can see from the triangle on the slide here that sine of the angle x over 2 is equal to u over root 1 plus u squared, and cosine x over 2 is equal to 1 over root 1 plus u squared. So this is very interesting, the way that we found some alternate representations for sine and cosine in terms of u. But to be honest, we don't often see sine of x over 2 and cosine of x over 2 in our integrations. So is there a way to find these similar alternate representations, similar identities, but in a more practical way? Clearly, we need to find a way to find identities for sine of x and cosine of x. And while that may seem a bit of a stretch from what we've just seen, it actually isn't. And that's because sine of x is actually just sine of the double angle of x over 2. In other words, sine of x equals sine of 2 times x over 2. So once we see this, we can apply the double angle formulas. And that's the real genius of this approach, whoever came up with it. So therefore, we see that sine of x is equal to sine of 2 times x over 2, and thus it's equal to 2 times sine of x over 2 times sine of cosine over 2, or 2 times, using our previous identities, u over root 1 plus u squared times 1 over root 1 plus u squared. And then multiplying that all together, sine of x equals 2u over 1 plus u squared. We can do this a similar thing for cosine x. So cosine x, or cosine 2 times x over 2, is going to be equal to cosine squared of x over 2 minus sine squared of x over 2. And again, using the previous identities, that's going to be equal to 1 over 1 plus u squared minus u squared over 1 plus u squared. And that substitution will be 1 minus u squared over 1 plus u squared. So this is very interesting, and it's really cool the way that we've been able to derive alternate representations of sine x and cosine x in terms of u. But it may seem a bit of a stretch to apply those two integrations. So let's look at an example. Let's look at the integration of secant x dx. Now, before we begin, it should be noted that there are several ways of approaching this integration, and the way we're going to approach it now may not be the way that you approach it when you do it, but we're going to take this approach just to see how we would apply these identities that we've just derived in the previous slide. So let's look at the integration of secant x dx, and let's change it a bit to, let's look at it as the integration of dx over cosine x. So as a reminder, these are the three main identities that we found in the previous slide. So clearly we can apply the one for cosine x and the one for dx. So using these substitutions, we can set this integration as the integration of 2 du over 1 plus du all over 1 minus u squared over 1 plus u squared. So luckily, in this division, we can basically cancel the denominators of both the fractions, and that leaves us with the integration of 2 du over 1 minus u squared. And that also equals the integration of 2 du over 1 plus u times quantity of 1 minus u. Now again, there are multiple ways of solving this integration, but for the sake of seeing how this approach will, will turn out, let's just continue with this approach. So at this point, we can use partial fractions. So if we look at just the integrand isolated, we see 2 over 1 minus u squared which is equal, we can set equal to a over the first root, 1 plus u, plus b over the second root, 1 minus u. And then with our addition, we see that it equals b minus a all times u plus a plus b over 1 minus u squared. And then with some math, we can see that a and b both equal 1. So plugging our partial fractions back into the original integrand, we can see that it becomes the integration of quantity 1 over 1 plus u plus 1 over 1 minus u du. Now, we can actually integrate this, and we get natural log of 1 plus u minus the natural log of 1 minus u plus c, or natural log of 1 plus u over 1 minus u plus c. Now we've run out of room, so let's move on. Oh, I'm sorry, I spoke a bit too soon. We can actually plug in the identity of tangent x over 2 for u. So we get the natural log of the absolute value of 1 plus tangent x over 2 all over 1 minus tangent x over 2 plus c. Okay, now we ran out of room, so we're going to have to continue on the next slide. Now, this was the natural log function that we got in the previous slide. So let's just isolate the input of that function. So it's going to be 1 plus tangent x over 2 over 1 minus tangent x over 2. Now we can change tangent to sine over cosine, and then to eliminate the denominators in both the numerator and denominator of the main fraction, we can multiply everything by cosine x over 2 over cosine x over 2, or just 1. So then we get cosine x over 2 plus sine x over 2 all over cosine x over 2 minus sine x over 2. And then if we multiply again by 1, or in this case, cosine x over 2 plus sine x over 2 all over cosine x over 2 plus sine x over 2, we get cosine squared x over 2 plus 2 times the quantity of sine x over 2 cosine x over 2 plus sine x over sine squared x over 2 all over cosine squared x over 2 minus sine squared x over 2. And then that leaves us with 1, that all becomes 1 plus sine x over cosine x, or 1 over cosine x plus sine x over cosine x. And then we can represent that as secant x plus tangent x, and we can plug this answer back into that natural log. And finally we get ln of the natural log of secant x plus tangent x plus c. And as you should know if you've done the integration of secant x dx before, that is the correct answer, so that's our final answer. Okay, now that that painful experience of sine cosine eliminations is behind us, let's look at hyperbolic functions. Now, in the interest of time, we're not going to be going into specifically what hyperbolic functions are and how they're represented graphically, but rest assured, if you're interested, there are plenty of great resources out there that you can go to and find out much more. Now, for the purpose of this video, we want to attract your attention to the contents of this slide. And this is a list of representations of hyperbolic functions in terms of e to the x. This is, as you can see, this is not unlike the equations that we had derived in the sine cosine eliminations part, but rest assured the applications are generally not as tedious. However, if you want to see an example of using these hyperbolic function identities or equations in an integration, you're going to have to wait a little bit, because next up is work and momentum. So we've now reached the final part of Chapter 5, the applications. Specifically, we're going to be looking at the concepts of work and momentum. Now, mathematically, work and momentum can both be defined as the integration of force. However, there's a key difference. Work is defined with relation to x, some distance or length, whereas momentum is defined with relation to some time t. Therefore, when we find work, we have to integrate f of x dx, whereas when we find momentum, we have to integrate f of t dt. Otherwise, the process is virtually identical. So let's look at an example for finding work. So here we have our work equation copied down, and we're going to be trying to find the integration from 0 to L of our force, which is sine squared x dx. Now the first step of this integration is to rewrite sine squared x using a double angle formula. So we know that sine squared x is equal to 1 minus cosine squared x all over 2. Now we can pull out the 1/2 and write the integration as 1/2 times the integration from 0 to L of quantity 1 minus cosine 2x dx. Now we can also split this up into two integrations to make it a bit easier. So we get 1/2 x from 0 to L minus 1/2 times quantity 1/2 sine 2x from 0 to L as well. Now we eventually get L over 2 minus sine 2L over 4, and putting these together, L minus sine L cosine L all over 2. So now let's look at a momentum example. And this is where, if you've been waiting for the hyperbolic example, this is where that comes in. So we're going to be looking at finding momentum when the force is defined as cosine hyperbolic t. So when we integrate from 0 to t, we are going to use that identity, that equation that we saw for cosine hyperbolic when we were looking at hyperbolic functions. And that's e to the power of t plus e to the negative t over 2. So overall our integration becomes the integration from 0 to t of e to the t plus e to the negative t over 2 dt. Pulling out the 1/2 and separating this into two integrations, we see it become 1/2 integration from 0 to t of et dt, or e to the t dt, excuse me, plus 1/2 times the integration from 0 to t of e to the negative t dt. Now, when we integrate and combine these, we make it it becomes e to the power of t minus e to the power of negative t over 2 from 0 to t. But before we proceed, we should note that this quantity e to the t minus e to the negative t over 2 is actually our alternate representation for sine hyperbolic. So really, this becomes sine hyperbolic t from 0 to t, or just simply sine hyperbolic t. And that's it. So before ending the video, we wanted to quickly go back to the table of contents slide and review. In the course of the past half hour or so, we've gone through basic integrals, use substitution, trig identities, integration by parts, trig substitution, infinite limits of integration, partial fractions, completing the square, eliminating roots, sine cosine elimination, yay, hyperbolic functions, and work and momentum. And while this is a very long and comprehensive list, your work has really just begun, because from here you need to go and do practice problems upon practice problems until you basically feel like the guy in the picture. And then and only then will you have truly grasped the techniques of integration. So, until next time, this is Arya saying good luck and peace.